For section 3.2, we're doing more operations on sets. There are three main topics for this section, where we're identifying partitions of a set, we're finding the Cartesian product of two sets together, and we're finding the power set of a set. With the Cartesian product, we start with two sets of numbers, and the result is a set of coordinate pairs. So it's a combination of all of the numbers from A and B as coordinate pairs, which we'll see in a moment. So say we have two sets. A has 1 and 2 as its elements, and B has the number 3 as its element. If we're going to find A cross B, then A is going to represent the x-axis, and B is going to represent the y-axis. So our coordinate pairs will end up being these. So first we look at the first element of A and combine it with all of the elements of B. In this case we only have one element in B. And then we go to the next element of A. So for the second element of A, we go through all elements of B and combine those. Note that if you have A cross B, it's not the same as B cross A. When you're trying to figure out the Cartesian product, it might be helpful to write out a table of all of the coordinate pairs before actually describing it as a set. So let's say we have these two sets. Try to list all of the elements of A cross B, remembering that the elements from A will be the x values, and the elements from B will be the y values. And with all possible combinations, you'll end up with 20 coordinate pairs. Here's the result. I've written it in a table where we have columns for B and rows for A. So notice that the first row is for the first element of A, and we have the coordinate pairs 2, 1, 2, 2, 2, 3, 2, 4, and 2, 5, where the 1, 2, 3, and 4, and 5 are from B, and 2, 4, 6, 8 on the rows are from A. The next item is the power set. In mathematics, the power set of any set is the set of all of the possible subsets, including the empty set and the set itself. So say we have the set XYZ. Our power set is first going to have the empty set, no elements, then all of the possible subsets with one element, and then all of the possible subsets with two elements, and then the only possible subset with 3 elements, which is the set itself. So for the set with the elements 1, 2, and 3, what is the power set? So for the set with the elements 1, 2, and 3, what is the power set? Okay, given these two sets here, what is the power set of the Cartesian product of these two? Well, first you need the Cartesian product of the two, which will be this set here, and then you get the power set of that result. So we'll end up with subsets that contain coordinate pairs. If having subsets of coordinate pairs, or even subsets of subsets, gets confusing, it might be helpful to come up with alias variables to replace those with, do the operation, and then put the values back in. So let's look at that real quick. Alright, so if we were going to find the power set of this, it might help just to sub these out. So I'm just going to say that let's use maybe y and z. Y is equal to 1, 3, and z is equal to 2 and 3. And so A cross B will be the set y and z. Now the textbook doesn't do this, this is just my own kind of thought process. Is if I have too many numbers going on, it's going to be hard to keep track of them all. So I'm just going to say, what is the power set of this? So we'll start with the simple one, that's the null set. Then we'll have one element each, so y and z. And then the only combination of the two together will be the two together. So it's simple, just having the two variables that you have to find the power set of. And now finally, to get it back to the original form, we're going to swap y back in here and z back in here and wherever else they show up. So we'll have the set, empty set, we'll have a set with 1 and 3, we'll have a set with 2 and 3, and we'll have the set with the two elements together. So 1 and 3 and 2 and 3. So maybe that makes it a little bit easier to figure out. Just swap out your coordinate pairs with variables, get a generic form of your power set, and then put your variables back in. Put your original form back in here at both these places. Let's look at this the other way around. Let's get the power set of A and B separately and see what the result of the Cartesian product is. So getting the power sets first and then doing the Cartesian product of the result would end up with this very lovely set down here. And again, if it is hard to keep track of all these numbers and parentheses and curly braces, then it might be good to just swap stuff out with variables. So doing this step by step, let's first get the power sets of each of these. So the power set of A is going to be our null or empty set. One element each for both of these, and then the set itself. And the power set for B will be empty set, and then the value 3, because it only has one element. Now, to put this together to get the cross value, cross product, we would have A, B, C, D. I'm just going to represent each of these elements with letters at first, and then we're going to swap it in afterwards. So, for the power set of A crossed with the power set of B, we will have, it's a cross product, so we're not going to have an empty set. We're not doing the power set. So first it is this first element and this first element. So we'll start off with A and E. Then we'll go to the next one. We'll keep A and go to the next element here, A and F. Then we'll go to the next element of A. We're basically just looping through all of the combinations. B and E, B and F, then C and E, C and F, and then we have D and E, and D and F. And then we will substitute these back in. So this all is equal to A is null set, E is also a null set. Okay. A and F, we have null set, and then the set 3. Now for B, we have a set with one element, which is 1, and E is our null set. And again, B is the set with just 1, and F is the set with just 3. Okay, so C, that's going to be our number 2, and null set, and number 2, and set with 3, and our D's. So we'll have, I'm kind of running out of room, we'll have D, which is the set of 1 and 2 together, and E is the null set. And finally, we'll have the set of 1 and 2 together, and our F set, so that is 3. And that's in how we end up with the Cartesian product of these two power sets. Okay, the last thing is partitions. So, with a partition of a set A, our partition is going to have multiple parts, and will cover all of the elements of A. So the 3 rules here are that for all subsets of A, none of them are going to be the empty set. Next, every subset that we list in the partition is not going to have any duplicate elements, so each element of A will only be represented by one subset or one part in the partition. And finally, if we were going to union all of the subsets together, we'll end up with our original A set. So for a given set A with the elements 1, 2, 3, and 4, some valid partitions are these listed below. There's not really a requirement on the size of each of the subsets, or the amount of subsets, or even if all of the subsets have to be the same size. As long as you have every element of A in the whole partition, you're going to have a valid partition. So for the set that contains the elements 1, 2, 3, 4, 5, and 6, come up with some partitions where for the first one, every part has the same size, and for the second one, no two parts have the same size. So for A, we can either come up with subsets of 1 size each, or subsets of 2 sizes each, or subsets of 3 sizes each, and we'll be able to fulfill that requirement. So here are some example answers, but they're not the only correct answers. You could have come up with something else. So make sure to go over the in-class exercises and the homework in order to get acquainted with these ideas.